feel the need to give you a few of mine. So why am I standing up here, right, and not you guys? Of course, you're going to be doing it out there anyway. I need to start out, I'm about 250 years old. So I've taught 25 years in junior high and high schools all over the world. I've been at university level. I was associate professor at Columbia University, and then I've been at Stanford since 2000. I always said that the PhD meant nothing to me unless it changed the life of kids in classrooms. I love all the sciences, but my favorite one is chemistry. So this is what we're going to do. I'm going to actually, instead of telling you what I think is a good idea to do, I'm actually going to have you engage in some science experiments, and there are a set of 6. They all have to do with water. So there's a whole stack of towels back there. I brought a whole bunch of paper towels as well, and so on and so on. And you've got trays to do them on. Although some of them, there's going to be spills. Okay. So in a little while, I'm going to, on your tables, you see this orange number here, what does it say?
Number 3.
Number 3. So number 3, and then over there on those back 2 tables, there's a whole setup that also says number 3. Okay, and so there are 6 of them. And the directions for each of the experiments is hiding under the stack of paper towels. Okay? So when time comes, you'll do that. I want you to experience that, and here's the directions. I'd like you to try to figure out what happened, how you think it happened, and how you know that, right? And in bold, on all of those directions, it says, and please do that with as little science-specific vocabulary as possible. You know what I'm saying? So, science teachers are wont to say things like hypertonic solutions, you know, as if that is self-evident. So, the point is to engage in talk, which is everyday language as much as is possible. So we're going to do that, and then we're going to come back, and I'm going to talk about how to deal with students in terms of doing this. And so there's a piece of writing that you'll get. We'll share out, so everybody will get a chance to hear a little bit about what everybody else has done. All of these will be posted on the web, so don't even worry about that. Okay, and then we're going to talk about pedagogy, and then did the session mean anything to you, and if it did, what did it do, or what could we do better? Is that one okay? All right, so without more ado, somebody from your group, you know, maybe a couple of people, come back and collect the material. Would you sit at one of the groups of tables, please?
Come join us, there's room at our table.
You need a lot of Did you find the original? Find the instructions. What? I mean, that's why we've got towels and baby towels all over the place, right? You've got more water if you need it, then there are more jugs of water back there if you need more.
More concerned about
Time out, time out. I didn't make it clear that these are 6 entirely different experiments.
Can you move it away? Move the balloon away?
Oh, there it is. Did you see it? Yes.
It was the whole
See that? It was so real.
do it again.
We got it.
I'd like to institute a strategy which is
Okay.
the board should always have some viewers.
All right. So let's do it.
Try to do it again. Start over again.
We're in a drought, man.
We're reusing them.
Can we try to get that again?
Yeah, we
For
have
prosperity.
that was only our test.
Ah,
Yeah, you're sticking.
wow.
You want me to start, because I'm kind of
Keep doing your
trying to,
I'm gonna move your stuff though.
I can't see it there to see what it hits.
Yeah, I'm getting this on videotape here.
Ready?
Wow, wait till you see your hair. Your hair is all stuck to the balloon.
Yeah.
You're good. You're
Hold
done.
off, Peter.
So wait a minute, wait a minute.
Wow.
Wait a minute.
Whoa.
Who are the observers?
We are.
I'm the timer.
We are right here. So you need to be looking at it like this.
Oh, you don't want us? You want us back?
I think if you're going to observe, you need to be observing it from the, if you would sit down.
More from this eye level.
We should have
You can almost, make it to my, you can almost.
So what kind of-
When it happened, I can see it there.
You need to be looking at the stream.
You want to get it?
No, 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 no. You're,
You're
this
gonna
is your
see the
group.
water move. I mean, it's very,
So you can see it.
I'm telling you, you can see it right when it actually happens, you actually see it. Ready? Ready?
Thin stream. There you go.
Wow, look
There
at
it
that.
is. Oh, there it is.
It's bouncing
It's
off right over
bouncing
there.
off.
What's
It's
it
bouncing. It's pulsing.
Pull it closer.
The static is going back.
There you go. A little bit closer.
Yes.
There you go.
15
It kind of
seconds.
resembles her hair. It's strange.
It's moving.
Oh, wow. Look at that.
What's it doing?
It's pulling itself.
It's bending.
Sorry, I'm trying to steady it.
Did you see that?
So you might want to stop it and recharge your balloon, you know?
Yeah, recharge.
So can somebody tell me what you guys are doing here? Anybody?
No volunteers?
No volunteers? So let me just take a video of that. Water and columns and air.
Comparison between whether we put our finger in at the end, second, and pull it up, or if we go down with it closed and then open it.
Ah. And what do you notice? Have you had a chance to notice anything yet?
Yeah, when you put it down with it covered and then open it briefly, it goes above the water line. The water will fill above the water line.
Oh, really? Can somebody show that for the tape? Okay, like,
It also goes above the water
could you do that again?
Yes.
Okay, so, yeah, I'm ready.
Down, like 1, 2. You can see it rose above the water line that was in the cup. And there's a few more particles than when you just put it in.
Thanks, you guys.
Yeah. The dirt gets drawn up. The dirt gets sucked right up. Yeah, it's like it's sucking from the bottom where here it's filling as it goes down.
So amazing. Thanks.
Your attention, Gutsy
Wow, look at what you guys. So you're doing the surface
I
tension?
just want to say, we should take maybe 3 more look at that one. Can I get right in there? And then, I want somebody to share out, which is a quick description of what you did. 1 and 3 minutes, if you could keep keep that in mind and designate somebody to do that. Thanks.
So what happened? So what happened? You formed a bubble.
Right. How did it happen? Water molecules stuck together?
That sounds like science.
Water fell in love with
So what's happening?
water fell in love.
When they say water seeks its level, that's what this means. Here. This is water seeking its level because it's connecting with itself. So the level keeps rising.
Okay.
So that's what that metaphor means.
Okay. Is there something surprising on the table to you? Is anything happening that was a surprise?
Well, maybe not a surprise to you, but it'll be a surprise to kids.
Yeah, the water was
Higher than the container.
That it's higher.
it was taller. It would be a surprise to the kids. Yes.
What is it? What's
I would
the
say the
surprise?
water was taller than the container. Overfilled the container. That would be the surprise to the
And it
kids.
didn't spill over.
Right, that it didn't spill. That didn't spill. It's
So
full.
that-
It's full, and you can put more. It looks full. It would look full to them, and you can keep putting it in. They would be like, no, I can't.
So, there's two pieces to this. The water is higher than the top, so it is more full than it was, right? And what, to your point, it didn't spill over. It didn't spill over. That's the surprise, right? It didn't spill over, which means we were expecting it to fall over. Why do we expect it to fall over?
Because we've seen that before. I mean, when you observe it, normally you're not absorbing it in this quite controlled quantity. You're seeing the bathtub flow over.
Why do you expect it to
Because
fall
that's what you've seen happen. That's your experience.
Prior knowledge tells you that you have seen liquid spill over when something is full. One of the first things we teach little kids is that water falls down.
Well, or
And
that,
gravity.
or that liquids don't have a form without a container.
They
So,
take the shape.
yeah,
But we always
exactly.
have it displaced. I mean, that's
But
what
there's
we
no
teach
more
the kids.
shape
That's
up
what
here.
the
It's
first
still.
thing we teach.
But gravity
Right.
is not turned off under this table. Right? Gravity is not turned off. So we would expect that water would fall down unless it was inside a container. It's not doing that, right? Which means something really important about the nature of water. What's already happening inside water to defy the force of gravity?
Yeah, it's got to have some type of energy holding it together. That at least at this point is stronger than gravity at that distance.
Something is happening inside water that's holding it together, right? Which tells us something really important about the nature of water.
Little kids would say it changed shape.
Which part? When she put the balloon next to the water was attracted, was being pulled towards the balloon, dancing towards the balloon.
Okay, this wasn't a regular balloon though. This doesn't
No.
happen unless the balloon.
Because we noticed that when she rubbed the balloon on her hair was also being.
Eric said the balloon was changed somehow after rubbing it on the head.
Right, and so little kids even know about static, right? Yeah. Right, and so the static of the electricity pulled the water to it. Does that tell you anything about the nature of water?
See, but the water wasn't standing still either. The water was moving also.
Uh-huh.
That water has charges.
There might be electricity.
Which is to stop people playing with it. You know, it happens in classrooms, as you know, as well. So I'm sorry to do this, but let's. I'm sorry.
You gave her a bubble.
I know, it's stupid, right? So let's have one person in each group do a really short, I'm talking 2 to 3 minutes. What did you do? What do you now know? How do you know it? Why did it happen? That kind of thing, okay? And if I could ask you to just nod.
Just like you were in the classroom.
Absolutely, thank you. All right, where's group number 1? Would somebody
Where's the group number 1 prize? Come on.
All right. Can you stand tall and talk?
Okay, so I'm sharing what we did. We had open containers of different sizes. Yeah, we were driving. And droppers, and we very slowly added one drop at a time. We observed that a dome formed on the surface of the water. We were surprised because the water was actually outside the container but not spilling over. How is that happening? We figure the water molecules must be sticking together somehow, and that there must be something holding the water molecules together, which, using a little bit more knowledge that we have, it's because water is polar, and it was stuck together.
So how strongly did water seem to be holding itself together?
Pretty strongly. I mean, you could overfill it, you know.
Compared to,
Gravity, which was the other force that we figured would be working on it, pulling it down.
so the water was defying the force of gravity by not falling down when we expected it to. So water must be holding itself up. Thank you. Thank you. That ordinary everyday language was phenomenal. That's great. Group 2. Aha. Who's speaking for group 2?
Okay, here we go. Our job was to determine how does different surfaces affect water drops. And so what we were given is different cups of water, different surfaces. They included a black plastic bag, aluminum foil, glass, 2 plastic covers that had cling wrap on it, and one was a blue and a black plastic sheet without the cling wrap to it. And so it was our job to observe the drops of water over time to see their height and to see how they behaved on these different surfaces. What we found is that they were not the same on each of the surfaces. So on glass and on aluminum, they tend to spread out very quickly, and when you put them very close together, they found each other very quickly and then joined together. And the black plastic and they kind of were a little high, but still were able to spread out. On the plastic garbage bag, they stayed as nice high little bubbles, so they kept their shape much longer. And when you would blow on them to get close, they stayed tall. They didn't spread out on the other surfaces. What didn't make sense to us is the cling wrap, which is plastic, and it should have behaved the same, and it did not. It actually spread out very quickly, and I'm totally confused.
You mean under the cling wrap?
Under the cling wrap.
Aha.
And the
Yeah.
cling wrap.
So yeah, they just literally, as soon as they put a drop on, it was no surface whatsoever.
Okay. So I fooled you. I did something to those surfaces because of what's coming up next. Right. But I need to ask you. So the description. Thank you so much. The description of these little beads of water. So here's the black plastic, and the water is just trying its darnest not to touch the black plastic. It's going, ay! No, it's pulling itself together. It does not want to touch that black plastic at all, right? So there's that force in water that's carrying on. I need to ask you something. Did any of you see, when you put the drops really close together, did any of you see anything odd happen after a few seconds? You did. What did you see happen? Speak up.
They ran towards each other. They clung together and formed a bigger bubble of water.
The water jumped over space. The water so wanted to be touching itself that this little water...
I'm not going to be saying that in my classroom. That's not going to go well in high school.
Middle school.
It'll work in middle
The water so wanted to be together that here they are discrete in space, but then one or both of them, it happens too fast to know, right? But all of a sudden, kaboom, there we go. Yeah. Thank you, group 2. Who has group 3?
We're great.
There you are.
So we had 2 jobs, and our first one was to find out if the amount of soap in water affected bubbles, and if so, how does it do that? And we found that it made a big difference. So if you had just a little bit of soap and a lot of water, you didn't get any bubbles at all. And the more soap that we added to the water, it was like the stronger the skin of the bubble was, so the bubbles were stronger and bigger and lasted longer. So it really made a big difference. And we thought the soap was kind of stuck together, and if we had more water, the soap couldn't stick together as well, and that's why we didn't get a bubble if we didn't have enough soap. Then we put a Petri dish and we put water in it, and we sprinkled some pepper on top, and we noticed that the pepper sat on top of the water and it kind of spread itself out over the surface of the water.
Excuse me, stop
Yeah.
right there. That was a fabulous expression. I don't want anybody to miss it. Tell us again, what did the pepper flakes do?
The pepper flakes stayed on top of the water and they spread themselves all over the top of the water. And then we touched the center of the water with a soapy toothpick, and it was like the soap made a skin all over the surface of the water and it pushed the pepper to the edge.
Like that.
Yeah, like that. Really quick. It was very cool.
So group 3, can you tell us anything about how soap and water are behaving together with respect to this attraction, this force that's going on in water?
They don't like each other.
Did you say they don't like each other?
They don't seem to like each other.
But they make a good match for a bubble.
They try and isolate each other.
Aha. I'm going to ask you again now. You're going to put yourself up for a minute. What is your evidence again that soap and water seem not to like each other?
Actually, we don't have that. The soap spreads over the water.
I'm not sure about that.
I'm not sure either, right. But let's go back to group 2. So underneath the cling wrap on those 2 surfaces, I had washed those surfaces with soap and water. And what happened when you tried to put a drop of water on a surface that had some soap with it?
Spreads out very quickly.
Is that evidence that water and soap are attracted to each other, or that they are not?
It wrecks the attraction.
It doesn't let the water stick together.
Yeah, destroys it.
Yes. So we've got some interesting things going on about, did you know water was so interesting? It's cool stuff. Group 4, where's group 4? All right. Do it, group 4.
We're doing it two as one here.
Yeah.
What does water do near a charged balloon and why?
So we Pia rubbed the balloon on her head for a long time, and then we had Josh that was pouring the water in a small stream. What we noticed was that the water started dancing towards the balloon, and it wasn't just the one big stream. There are like 3 little streams that were trying to really get to the balloon. And as Pia moved it, it started to even dance a lot more. So it's really neat to see. We said,
Excuse me, can I ask you, is there any connection between the part of the balloon that was rubbed on the hair and the balloon vis-a-vis the water, when the water was dancing?
yes.
Yes. What we noticed is when the balloon that was not rubbed upon the hair or had lost that rub upon the hair, is the water went back to the normal stream. It didn't dance anymore.
So what part of the balloon caused this behavior in water?
That we talked about the electricity, you know, this charge, the static electricity, right?
Thank you.
That was That's it.
Was that
I know you said thank you, so I said. You said thank you.
I'm sorry.
That's fine. You got it.
Let's hear it for group 3. Group 5.
group, we wanted to find out the affair between water and a column of air. So what we did was we placed a small amount of moist soil in a glass, in a cup, and then we added a lot of water. And then we lowered this glass tube, which is open at both ends. And then we covered the top with our finger, raised the tube, and we found out, we observed that the water level inside the tube was the same level as the water in the cup. And then we changed how we cover the top. So this time we covered the top of the tube first, then we lowered the tube, and then remove our finger quickly. Then we pulled it up. Then we noticed that the water level was higher than the water level in the cup, and this time also there were soil particles inside the cup. And so
Inside the tube.
So, Tomorrow, there were no water particles in the first, I mean, no soil
there
particles?
were no soil particles. And then to verify what we saw, so we started adding, we added food coloring, so it will give us a better picture of what happened.
Do you have any sense in your group as to why that happened? Or what it is that happened?
So
Let me tell you why I'm asking, because group one found that water had this capacity to defy the force of gravity and not to fall down when it should have done, you know? And here you are holding up a column of water, right, with your finger on top of a glass tube, right? And it ought to be falling out of the tube, right? But it's not, right? So did you have any ideas in the group about what was going on there? Yes.
So when we put the tube in first time, without our finger on it, we figured there was air in the tube before we started. And because our finger was off of it, the air went rushing out of the tube as the water filled up. The second time, we had our finger over the tube, and so that air stayed in the column. We put it down, then when we lifted it up, the water came rushing in, and it came rushing in with so much force, because as we've just learned, it stuck together, I guess, that it went up higher than the tube. And something else we talked about was, why didn't it have dirt in the first time? And we figured that the water, we were collecting samples of water from the surface of the water, and then as it went down, so basically we started at the surface and worked down. The second time, because the tube was at the bottom when we released it, was collecting samples from the bottom, and the evidence was the dirt in the tube.
Yeah.
So then, why did the water go in the tube to begin with?
Because there was air on the outside
Absolutely.
pushing down on the water.
That's what I would ask.
Yeah, of course.
Because there was air on the outside that was pushing down on the water and forcing the water up into the
So the
tube.
pressure on the surface of the water was such that it forced the water in the tube to rise. Yeah, exactly.
The evidence for that.
The evidence?
I don't see evidence for that. I'm just gonna ask, because see, when I put the straw in,
I love
the
it.
water's coming up as I go, so there is no real evidence
No,
of any other force.
But when you've got a tube full of air, and you put it down in there and so on, so there's nothing in the tube but air,
Okay.
which you can see better when you've done the food coloring, I think, right? There's nothing in there until you take your finger off the top, right? The water rushes up that glass tube with such power that it actually rises above the level of water in the tube itself. You could see it in the glass, you could see that, right? So I would argue, I think it's a lovely question. I would have to argue, depending on the level of the students, that something pushed the water into the tube. And then I'd have to go to a place of saying, what else was touching the water except air? You know, I mean, it's a lovely form of argument, actually. But that's where I go. Thanks for that question.
If the amount of air that was in there before you raised it, because it's less than the water, the air that's in the tube already is less than the pressure on the water. It's sort of that experiment where you light a candle and you put a glass jar over it, and then the pressure, some of the bubbles escape, and so the pressure inside the jar is less, and so it fills up with water.
How many people know that experiment? Right. I'd like to revisit that experiment because it's been misanalyzed all the time, and so because really what's happening is that the candle heats up the air in the flask and drives the water around. Right. Because the candle uses oxygen, but it also at the same time produces carbon dioxide. Right. So hold on, we have one more group.
So we were going to tandem explain this one because we found out that one of our members has a flair for this demonstration. So we also found that that water has a particular force that we never slow down to recognize. So if you were to place the paper on top of the cup of water, you can flip it over and it sticks. But then we found that after a while, our paper got so wet, it couldn't hold the water anymore. So we tried it with different shapes of glasses. We tried it with different size of note cards. And then when we're, not to steal the thunder, but you could go like this and you flip it all the way around. And our front row students in our group were quite nervous, but we had such faith in our teacher that we knew that he would do it so well.
Show me a trick, show me a trick.
But the first time it worked perfectly. Then we tried it once with a beaker that had a lip, and we weren't sure. It just didn't work, and so we couldn't understand why the water wouldn't stick to the note card anymore. So we came up with a bunch of different applications. So we're excited about it. We couldn't stop talking about it. So it was a great demo. So thank you.
Thank you. You use different size containers, different diameter containers, and different size.
Well, and then our lovely demonstrator actually has a trick. Do you want to show them here with the card?
What a trick?
Oh, yes. These people have paid good money. They drove a long way or so long.
I mean, the trick is basically is about, it's about teaching is about preparation. That's all it is. And rather than like one piece of paper, you do like 3 pieces of paper and a small piece of paper in the middle, and all you do is you withdraw this one out and say, hey, you see there's one thing coming out. So basically, you withdraw that out, and supposedly the water drop out. Maybe check this one out, they still stick. And if you want to prepare another one, you can pull out another one. This is a clean one. But actually, you put the two in the middle between the other. It's like a sandwich.
So we had a lot of fun with that.
I love it. Good. Thank you. So, one of the challenges in doing this session with you was that among you are K2 teachers, 3-5, 6-8, and 9-12 teachers. The 9-12 teachers are often biology, and not physical science. And so what kind of experiments and phenomena to bring to you that would be engaging was an interesting challenge for me. And then to try to put it in a bag to bring it from Palo Alto on the plane. Another thing, right. So, this is what I would do next with children. What I would ask them to do is to write in narrative form, in their own way, what they did, what happened, right, and how do they know. I'm specifically wanting to get away from the strictures of the formal lab report, right, because for those of you who have tried it, you know that is, students have difficulty with what to put in which section, right? It just drives them crazy. The other thing is, I don't know if it happens at your school, but I've done in chemistry, we've almost given up the whole notion of coming to a conclusion at the end. It's mostly about data tables and error analysis, and as one of my chemistry teachers says, error analysis, it always comes down to human error, so So the point about this is to write a narrative form in ordinary everyday English, and so on. So I have one to give you to look at. I want you to read it, and it's about experiment 1, okay? And I would just like you to read it and give me some feedback on that for a minute.
I think it's right about time to get started. and it is 9:45. I will try to keep us on schedule, and let me just start by telling you who I am. Some of you know me. I'm at Cal State Fullerton. My name is Mark Ellis. I'm in secondary education there, so I work with pre-service teachers, and also right now I'm actually working with all credentialed teachers on different projects that are grant funded. So I'm out in schools a lot, working with math teachers and science teachers to some extent. And for the last 5 years, we've had a project working with teachers to understand what are the Common Core standards, what does it mean for my practice, and then how do I support other people in my department, in my district, in learning about these. And one of our members of that project is here, Jenny Kim, is part of that project. So she's been with us for 4.5 years studying this stuff, so happy to see you here. So what I was asked to do about a week ago was to prepare something for you all to engage you in some of the shifts that we've been talking about. And so I'll just tell you up front that I've done this in a very small scale way with a group of teachers last week just to test it out a little bit, but I've not done the whole thing. So I'm going out on a limb, and I hope you enjoy the trip with me. And I don't think the limb will break, but I think we'll have some fun. I want to start off with just this little video clip that I found on this site called YouTube. Have you heard of this? Oh my gosh, like there's so much out there. So this is a clip from a New Jersey news station about the carnival events out at, or the carnival games out on the New Jersey boardwalk. The Jersey Shore, is that what we call it?
Jersey Shore.
Yeah. No slippery.
These guys are from the Legalized Games of Chance Control Commission. It's their job to keep game operators honest. Whether it's conveniently askew basketball hoops or darts with dull tips, investigators have seen it all.
We've seen bushel basket games, which is a softball that has to be thrown into a tub. Operators may put a tennis ball or a doorstop behind the bushel basket, making the back of it springy so that the ball cannot actually stay inside of the tub.
It's a for-profit business, and they expect to make some money on it. But by the same token, there has to be that ability to possibly win. You just can't rig it so that they can't win the thing.
Most of the time, violations aren't so blatant. Maybe an operator holds on to change and lets you play another round. Or the prizes promised aren't actually available.
This dart lost its spin.
Okay.
Required to have it spin.
All right.
Okay, we'll put that in here.
Well-established, family-friendly boardwalks, like this one in Point Pleasant, are more in compliance than you might think. But for a long-time investigator, a violation sticks out like a sore thumb.
Investigator went up earlier and he found that several of the rims were not level, and that gives an unfair disadvantage to a player.
Yeah, that was pretty egregious, that basket. Just walking by, you can see that.
So just real quickly at the table, talk about what is a fair game then. Just real quick, what's a fair game?
The probability of Vegas, like if you only have a one.
That's not what they're talking about. They're talking about skewed. Well, maybe it's because they're not skewed for the health
Okay, so I heard a few things. I'm gonna interrupt because we'll continue this conversation for the next hour or so. What were some things that came up about this notion of a fair game? What were some comments that came up at your table? Yeah.
Well, that there has to be the opportunity to win.
The opportunity to win. Okay. What else?
We were saying that it should be like 50-50, equal chance to win or lose.
An equal chance to, what do you mean equal chance?
Like, 50% chance to be able to win or...
Oh, okay.
But nothing was mentioned in the video about equal chance. There just had to be some possibility. It didn't say what the probability was.
Okay, so in this real life example, right, their concern, these investigators' concern, is that it's possible to win the game at all, right?
Yeah.
Is it so rigged, as they called it? What's rigged? What does that mean?
Something to sway the outcome.
Manipulated.
Manipulated, skewed, right? So it's so unfair that you actually can't win. So that's really unfair. But in a mathematical sense, as you're suggesting, maybe there's this idea of 50-50. Yeah.
So I was thinking now about the basketball hoops, even if they're unlevel, there still is a chance to win, just the chances are decreased. So.
Yeah. So as the investigator pointed out, hey, they got to make money. It's a for-profit business, right? So clearly, if you're running these games, you probably don't want the odds to be 50-50. Maybe you want them a little in your favor as the operator or owner of the games. But what we're going to do today is investigate an activity that will get us into this idea of the mathematical notion of fairness. And so we're going to explore that. I'll show this again at the end so you don't need to worry about it. And I'm happy to share all the slides with, I don't know if Melissa maybe can put them on the Edmodo at some point. So don't worry about writing anything down. But here's the game. So Amelia invites her friend Bartholomew to play a simple game. A bag has 2 blue tiles and 2 red tiles. She shakes the bag and asks Bartholomew to take 2 out without looking. If the 2 tiles are the same color, he gets a point. If the 2 colors are different, then Amelia gets a point. The tiles are put back in the bag and another round is played. So the question is this a fair game? I would like you to take time at your table with your groups to investigate. There are tiles, there are bags, so feel free to use the materials. And you may want to collect some data about this. Let's take about 3 minutes to generate some initial impressions. And initial impressions, are you thinking it is fair or not fair? Not? Yes?
Maybe take tiles without replacement or with replacement.
Yeah, that's what I was
They think
thinking.
exactly as right.
2 tiles.
I got it too. So I'll let you decide.
So without or not with replacement, not replacement. So not replacement. Without replacement.
First degree,
Because this is not Marlene involved, my involvement. How close the gate? She picked 2 things and So now I get 2, right? So I get 1. I got 1, right? So how many tiles are we going
which is funny because they're going to it off to the right. So we're having a video.
We should just have seen different
So far.
This is not, yeah.
So, for our together, you had one teaching, right?
So let's just share some initial data. Those of you that have been playing the game, if I can just, I'm going to interrupt. So just to get some initial data, what's your initial data? Those of you that are playing the game, what's the data that are generated? So how many times did same come up and how many times different? So what do we got? Let's start with the back table.
We did 10, and we got exactly 5 and 5.
Oh, you did? Okay, 5 and 5. So it's a fair game.
Well, the result.
Oh, okay, we're not done yet. Okay, let's get more data.
Ours was 9 different, 1 same.
Oh, so they had 9 and 1. Okay, what else? Another table?
We had 2 same, 8
2 and 8.
Or we basically, so.
Okay.
Yes, 7 same and 18 different.
7 and 18. Wow. Okay, the back?
We had 1 same and 7 different.
1 and 7. How about the middle?
10 and 5.
10 same. 10 same?
Wow.
5 different.
Go to Vegas.
Is there another set of others? Okay. So, who can sum these up? Number talk? I only really want one way. This is a different task. So what do we see here? 26. 26? Same?
Yeah.
And?
He said
52?
Oh, wait, I left one out. Where's this one?
Huh. So does that look like, just on the surface, does that feel to you like it's a fair game? No.
It's fair because I'm winning.
If you're Amelia, sure. About how much more are we winning, right? About twice as much, right? Or half as much if you're trying to find the same. So there's some sort of mathematics behind this that we're now going to start exploring, and some of you have gotten started on this. So what I want to do is ask you, you've done part 1, is figure out, is it fair and how can you be sure? So we kind of have an indication that something is not quite right if we're trying to have a fair game. And then once you can mathematically agree as a group that, okay, it is or isn't fair, here's some mathematical evidence, here's an argument that can substantiate our claim, then start to think about, well, what quantity of each color would make it a fair game if it is in fact not fair. And I will give you a worksheet that you can read the directions on. And part of the directions is this slide about working together. Now, if you were my class, right, we would have established this at the beginning of the school year. When we work together, remember that it's about everyone's learning, and we all have to understand any solutions that come about. So if someone in your group says something and you don't understand it or you don't agree with it, please ask. Right? So work it out within your group before we share out with the whole group. So I'll hand this out. It has the exact same information on the handout. So now your task is to do what?
To justify our answer.
Discuss what?
Whether-
Okay, is it fair or not?
And how can we be sure?
How can you be sure? Using
Make it fair.
mathematics, right? Mathematical argument. And if you determine it's not fair, how could you make it fair? What? And by changing the numbers of piles. So there's your task for the next few minutes. I'll hand these out.
We're still not decided on a definition of fair. Are we shooting for 50?
Oh, that's a good question. What are we calling fair? That's a very good question. What do we see as a mathematical definition of fair? Fair for the people playing. 50-50, what's another way we could say that?
Equal opportunity for both of them to win.
Equal what?
Equal opportunity for both.
Equal opportunity. So opportunity could be described how mathematically? We could describe it as probability. So the two probabilities of having the same or having a different would have to be equivalent. What else could be equivalent? You could play around with a point value. For this particular one, I want to ask you to play with just the quantity of the tiles, but that is an excellent strategy you could also use if we gave the person that had the same twice as many points, right? That would kind of even it out. But for this, we're going to play with the number of tiles. What else could we do to determine whether it's fair? So we had look at the probabilities. You could adjust the points. What else can we look at to determine if it's fair?
Change what determines winning.
Oh, you want to change the rule? So we're sticking with this game.
That's right.
You could, but we're sticking with the rules. Well, what determines the probability? How is it you're going to figure that out?
Whether or not you replace them.
How do we figure out probability?
The number of positive outcomes over the total number of outcomes.
Outcomes. So look at the outcomes. The number of outcomes. If I'm the guy getting points for the same, and you're getting points for different, what better be true about the number of outcomes that are the same and the number of outcomes that are different?
It should be the same number.
We would hope, right? So you can look at probabilities, you can also look at outcomes. So think about how you would represent those. That's the challenge you have in front of you. So how are you going to represent this information? So you can then mathematically make a claim.
That over time, definition of fair.
So I was saying, so if you get a blue, that's equal opportunity. To get, right, because we had but your first right. But if you
But you now are adding a chance of getting the blue extra chance of getting the same. Because you still get 1, 2 opportunities when you pull up and get one of them. One other chance.
Three opportunities again.
One opportunity to get the same red, but to get the blue, you have 2 opportunities to get the same, and 2 opportunities to get the but it's still unbalanced line because you took the red, now you have still the
Sorry? Yeah, you add another red.
Right. Yeah, so by it's red. Throw back. Now you can choose another red. Now it's fair game. The issue here is that when you close to at the same time, essentially you pick the first one, that tile is gone, and so now there's only 3 left in the bag.
How do you you're saying probability like total outcomes to the favorable outcomes we have? How do you
You'd have to change how many of it. Just say 2 tiles.
That's changing the rules.
So like you were saying, you gotta change the rule, saying like add more blues, say if you get more blues.
Add more than one. So what is it, if you get two of the same, another blue?
So that's
So you take one blue,
Okay, so now you're down.
your favor is positive.
There is basically one-third chance to get the same.
Yeah, okay, all right, so 1/6 to get the first. Show me. Now you get 3 and 3 and 5. So the yes, 3/5 and 1/6, and 1/6, so a 10% chance right now of getting 2 gifts versus.
Wait, 10% chance you get another blue?
Yes, you had 1/6, and then you had 3/5.
I think it has to be more blue than red, right?
There's 6 reds.
So what about 5 reds?
It's more possible.
So Beverly has 5, yeah. 2 reds.
Right.
Okay. Then now you take 5, 7.
outcomes would be the best.
You think?
So what happens if we still there? We take it, we throw the ball back in.
You guys figure out what we have to do. Yeah.
Why is this
Both of the blues. Blue number 1 and red number 1. Blue number 1 and red number 2.
21.
Both of the red.
But you're down.
That was going to be the question. These labels, what happened to
This chance
whole
of
red
winning
two?
is like 1 over
3 blue out of 5.
That's red.
So I have 5 is it like that's 4, and then you have 4 left. 4 and 6, which is
So there's 1, 4, and all of us take
The red two turns out to be.
So now,
Did you just say 5 times 2/3?
or red.
Yeah, you're going to have that.
Oh, yeah, sorry. Yeah, and the other one's 2 7 times 6 because they're 2 red,
Really
right?
smart.
Probably
That's
pulling
the
out
place to get to.
or whatever's left.
I wanted to know.
And so just from that, did you establish whether the
That's pretty close, so you can hear it.
What if we didn't increase it again? We do 5 or 6 blues and 2 reds.
Because right now Bartholomew,
It's almost 50-50.
this is Bartholomew, and it's over 50%, because 50% is 21. Yeah, yeah.
Right, so let's do
6 blue, 3 red.
How we done?
We're almost at maybe equal.
And what is that?
That's the five or something.
Oh yeah, 360 with the 2 power. So if we
A way to draw the outcomes?
Well, we
Represent
see
the
where
outcomes.
so we're like, I got using them all.
So this, if I understand correctly, what is?
Ask Cynthia to share a drawing that they made, a representation.
You got the other half of the discussion on that too, though.
That's okay.
We're still talking about it.
That's good, that's good. That's okay. And I will get this going, so I'm really high tech here, okay? Yeah, it'll face you. And we can zoom it out a little bit. There. So can you just tell us what that represents?
So we actually decided to add a third blue. So we had 3 blues and 2 reds, and in just playing it 10 times, we ended up coming up with the more equal or fair outcomes. And so we're still discussing whether or not this actually shows the correct representation. So I went ahead and just wrote down blue 1, blue 2, blue 3, red 1, and red 2, identified those. And if in the bag you had chosen 1, it could have been blue 1, but then you had these 4 left over to
to choose as well as part of your second. So we came up with 20 total possible outcomes, and of those 20, 8 times you would be able to get the same color.
And so is it fair if it's 8 out of 20?
That's close.
It's getting closer, right? It's closer, right? Not quite there.
Right.
So I appreciate you sharing that, and this is an example of using a tree diagram, right, to represent outcomes. Another way to represent the same situation is to think of this as a table, right? So across the top, we have one set, down the column, the same set. So I can't do B1, B1 because it's the same tile, right? So this diagonal we don't count. But what would this be? B1, B2. It would be the same. So you could write it as BB, or you could just write it as, I'm going to put an S. Thank you.
Okay.
For the same. What would B1, B3 be?
Same.
So you have another one the same. B1, R1. Different. B1, R2. Different. B2, B1. Same. B2, B2. Remember, we don't count it because it's itself. B2, B3. Same. Different. Different. Same. Don't count. Different. Different. Now we're in the red, right? Red 1, blue 1. Different. Red 1, blue 2, different. Red 1, blue 3, different. Doesn't match with itself. And here's the same. R2, these are all going to be different because matching with the 3 blues. Red 2, red 1, same. And then again, our diagonal we don't use. So does this agree with the same outcomes that she was representing, that Cynthia was sharing from her group?
Yes, but I don't think that represents what we're doing. I think, and that's where we were getting, this is if you're picking one tile and putting it back in the bag.
Oh,
It's double dipping.
It's not paying attention to it's thinking that order matters. So if I take 2 out and drop them on the table, the one on the left and one on the right, I say R1, R2, or R2, R1. It is counting them twice. You're right.
Okay, so
you could make the argument that we only need half of that chart, and that would be a good discussion to have at your table as to why or why not that is okay. But yes, I do understand your point. But how many outcomes are represented in that table? Well, we have 5 across the top and 5 down the side. 5 times 5 is 25, but what did we leave out? We left out the diagonal, we left out 5. So there's 20 outcomes. Where are the 8 that are the same? 1, 2, 3, 4, 5, 6, 7, 8. So this is another way that you might think about generating a sample space, which means all possible outcomes as you explore this problem. And notice that they changed by adding an extra blue. They kept the number of reds the same. Try some other combinations. And I am gonna, I'll let you play around a little more, but I'm gonna come around and give some more directed suggestions on certain quantities to explore.
For the same.
Interesting. No. That's good. That's what we want to do. But you can't be the only one in your group doing that. So the group has to understand that. If you want to use that. So connect it to perhaps what is showing there. I'd like that connected to some other representation, so it's not just sort of off by itself.
Doesn't seem like I just doubled the I did 4, 2, and it doesn't seem like 1 of them. The probability of getting them to be the same. If you do 3 times as many as a pair,
Every time you just leave it and let it run like this, in a few minutes it's going to turn itself off. So what it happens, I just turn the switch on off again and it restarts. But is that...
Yeah. Right. No, that's great. That's great. But be sure that your whole group understands how those things.
Five.
Yeah, but it would just be.
No, I did five.
It'd be a positive because when she's live,
The number is.
we didn't take a point away from her.
Every time you're adding two of these, right? And then you're adding
Just
how
getting
many
way
other
closer.
these.
But that's why they said
The bottom you also
yeah, that's what I said. Yeah, if you go, right, because if you go like that.
If you stay consistent, the
I'll
S's
tell you,
keep
but then
getting
like, oh, wait, you
bigger or bigger.
lost
So you go, the number of blues, you take away, because it's 5 blues, but 4, 3, 2, 1.
Oh, hold on. Like if you add.
Right, so now if you added additionally more red,
You get two.
One,
You bet.
five, right?
10, 11.
And then this one is going to just be 1, 2, 3, 4, 5. 5 times.
Yes.
Double right because the number of blues are 5.
There's three, one color.
Right.
And then you have like an extra one. That's constant. So these are variable and these change.
No, it would change. We added R3, R3. So then it would be
And one red.
same.
No, they did 3 and 2.
And the same.
Here, add 4
And
to
here,
it.
you're
And that's if we're just
This is just the example, this is using numbers, but now I'm switching to records from numbers to symbols. Where did we have,
here, there's
where did we
two.
have when we were so used to redoing it when we had
One is different.
6, 7 blues and 4 red was really, 9 blue and 5
And I
red.
realize
Yeah, so it does, if you add extra red, then you start going to,
How can you use that to generalize to find? So that
same, same.
That's what it's, that's the next step.
Right, yeah.
So now you.
So where are you at right now?
5 blues, 3 red.
No, how many S's do you have?
Instead of 2 more, the 13 S's. The difference is we have 15. Before it was 11 S's.
Because you've been doing something that's the same.
So we try to make this ratio 50-50, right?
So 11, 10 is
That's why I'd like to ask you.
once you flip to the other side, you should be moving further right.
So I think like you're trying to do with an equation, you're trying to see the pattern, right? Between the number of blues to how many similar sames you come up with.
So the equation comes from, you know how we're having probabilities with 5 blue and, sorry, 7 blue and 5 red. So instead of using specific numbers, I just use B to represent number of blues.
Right.
So the number of blues here decrease by 1 because, and then the number total is just blue plus red. So this is -1, right? And this is the picking red. This is red. Right. And then I just, the bottom is the same, and then we'll square red. What is that? Is that an R? Yeah, it's an R.
2BR. Wait, what did you do?
I just did squared, B just B squared, because I'm thinking it's minus R. This is a whole here. It's like X times X minus 1, right? And then the top is just B squared minus B. And I just use I just
We wrote it out. What's the mathematics?
This is squared minus B plus R. This is not squared. This is B.
They're playing your game, them thinking they're gonna win.
Yeah.
It's a bracket. So she's doing this thing here, but she's saying this X.
B plus R, R, minus 1 because we're taking away 1, right?
And if you
So
try
then,
to figure out a place.
what's the probability? It's
So the goal is to.
Sorry.
We're still working.
Right here. Times B plus R. So that's the probability of picking a blue first time. And then we did B minus 1, because now you take away one B, and B plus R minus 1. But for purposes of multiplying, you group like this, and group like this, but we're making like that. So it's like X times X minus 1.
I know, me too.
B plus R. Times R minus 1 with the B plus R, so
Right,
take
so
away
then,
1,
and then
that's
this
just
would be
like that.
n minus 2.
I guess what we'd have to do
We look it up to square, multiply it out square.
we should have had it
But n choose 2 and
like the original one.
So you take the denominators.
is n times n minus
So we multiply these together, it's B plus R squared. And then B plus R minus times negative 1.
Right, what I'm saying
B.
is n
Which makes it equal just half probability. And then we did,
Okay, so that was, the original one
we did
was
probability.
gray, was
And then round, and then basically we just organize it to B squared plus R squared minus B plus R.
Well, when it was, so yeah, there was, there's 4 total. And there's 4 times 3.
Oh, yeah, and then that's awesome.
Right.
So that was what we had. That here, right? We said there were 6, and then when he numbered it, the extra 3 to 12, but by numbers, it's really saying that 2 is different from 2. So this is where.
Wait, hold on. Is that what we did?
But I'm still.
I don't think we have to
Oh, it doesn't be half, right? No, it doesn't.
Oh, I don't know. Does it? What's the calculation?
It sounded like you wanted to.
What's the calculation?
I guess what I was
Check
thinking
it.
now is in order to.
So I see you have some probabilities.
I don't know.
Yeah, so we just said 3 blue, 1 red, so we should got it probably.
Get the same color.
They're good songs. But I think you want to look at the relationship between these. You went from 3/4 to 2/3. And so how does this relate to this? But that's not the same. But I mean, if you were to make it drawing 0 or the 1 and the 3 case,
So this is really
what would it look like? And how would those be?
Because you either have the n 2 x's or you have 2 y, there's no overlap.
For each one, we have 3.
And then for different, it would be x choose 1 and y.
Because it's, you just move the B plus R to the side.
Thank goodness, that's what we got a minute ago.
So,
This is still.
so where do you see these?
No. It doesn't have to be x
Yeah, but that's
y.
like considered this one.
It would have to be, oh, that's what it is. So the second number is n minus 4. Because we don't need a second number.
So your question is
Y equals
But it's red.
n. There's 5 total and 1 blue, but there has to be right.
Yeah, that's why these X's are there. Right?
Yeah.
So if it was 3/4 times 3/4, you have all three. That means we're allowing you to duplicate, putting them back in again. But when we take these out, it reduces the value. Right? So that 3 times 2 should be equal to 6 outcomes. So what you want to think about is how can you, instead of using actual values, how can you use variables?
You're going to check now
So
and try
like
to plug in
take
probability.
the number 3,
Like what else can
and instead of using 1 for red, what can you do?
This is the 3
Try and generalize that.
There would be 3 to
think of the mathematical relationship between the two.
Plus you can have
How we doing?
habitat and a quarter tile. And because you're taking two, you have choices.
Like when I originally,
There's no way you can get it
you know,
before.
mathematically, it's not working. And so we were saying like 1/3.
Which is okay, sure.
And then.
Which is the same as 4/12 and 8/12.
Right.
Probability is seventh grade standard now. It used to be like 6th grade. 9, 6 out of 9.
I don't think they're gonna ask them to go this far, but come up with something at least rational. I think we did it on the table.
Yeah, I mean, I'm thinking more when we look at the outcomes than the probabilities, because you want an even number of outcomes.
Yeah.
What's going to be a number of outcomes? The question is how do we generate these outcomes?
Okay, so
generated
the way we were doing it, so let's do it.
So we're saying we just had blue, and blue, and why did that work when it was 5/3?
Right.
Because the equivalent fraction should be the same ratio.
Try 5.
But we did that earlier and it wasn't the same.
I thought we didn't win that.
We did, I added the.
You did? I thought we did 5
So should we do 10? See if it makes a difference.
Yeah, let's do 10-6 just to see if it works. 10
blue, 6
That's minus, you get a recession minus intersection.
Maybe we just messed up on
Oh, I think it might make a difference in terms of the quantity.
Give me 5, 6.
Total 12, right?
Can you explain that?
So, how many 6 were saying? How do those numbers relate to?
I know, I was just gonna say that, yeah.
I know you can draw it out, but if it's one you wouldn't want to draw.
So what did you do?
So,
See, I can't figure it out, because you have this eventually, okay, so you're gonna give me.
okay. So, R5, R6.
They're not just having.
Yeah, let's get a blank for it.
how are we doing?
We got.
We think we got an answer, to make sure that it's right.
You think?
Okay, because it works with the mathematical equation that we have for something. Yeah. But we want to just make sure.
So tell
that-
me the equation, I'm curious.
I'll let her tell you.
I want to hear from someone other than Joy.
In our equation,
So we need R5, R6, right? Okay, that's why we got it.
Which now I'm like, it's so.
Oh, yeah.
Which is either right.
Tell my principal. I need more money. So where did the formula come from? What's the relationship that you all came up with?
Well, we were calculating.
Basically, we were doing initially the small trial where we did like a probability of picking one blue and then picking the second one as another blue, and then so instead of doing numbers and keep practicing and just trying guessing checking with different number options, we said, well, what's basically what we're doing is then we put in a variable to say, well, what if there's any number of blues that we want to pick? So that's where we came up with our equation, basically saying instead of the numbers being there, replace it with the variable that would represent the
Okay,
number
but
of
where
blues.
did this relationship come from? Like, where did that come from?
well, no, because
That's the same as our probably sample space. So that's probability for getting blue.
Is this?
Yes, and then the probability out of the total outcomes. Yeah.
And so it relates to like the diagram there?
Yeah, this would be
There's the probability of getting a blue
any
of all the blues and reds, probability of getting another blue.
Take one out, so we've already picked one, so that's where the minus 1 comes from. And then the total is the number blue plus the number red. And then, so after you pick the first one, you have the number blue plus the number red, minus 1 because you've already picked it with one tile.
Well, in terms of the chart, the -1 is whenever you match up the same tile, that one tile is
That's
gone.
at -1, the X.
And so this is a process of saying these need to be equivalent to 50/50. And you chose to work with which of the outcomes? This is representing the same outcome or different outcome?
We're going picking the same.
Same, okay. Could you have picked the different outcome, like the outcome representing different?
Yeah.
Oh, is it?
Well,
Well, you can just do one line, right?
Yeah.
Right. But I mean, if you were to set this up instead of finding the same, what does that look like for the difference?
Because they want to be different, right? Red, B plus still be minus one. And then you can double it?
Think about that. I'm stealing your marker.
That might
Okay, so I want to have us look through an example here of how this might play out. And I introduced earlier this idea of a sample space as an array or as a rectangular grid, kind of, right? When we were doing the example of 3 blue, 2 red, suggesting that this is one way to organize, not the only way, but it's one way to organize. And so many of you are using tree diagrams, which is great, and some of you are labeling the probabilities on them. So does anyone have a question about what that represents? Just take a look at it. And I realized I didn't multiply them out and reduce them, I just left them as products. So could someone explain to me where this shows up in the sample space? What's the connection?
Can you say that again? I'm sorry.
I'm just picking a particular branch of my tree, so that would be blue and then red. Probability of blue and blue-red is this. Where does that, how does that connect to my sample space? Which is
The ones that are not boxed in.
it will be 1.
So, blue, red.
Those are the ones that are different, so they're not boxed in.
Blue, red, blue, red, blue, red. Find out?
10.
10 or? 3. So you could have 6 blue, 10 red, 6 blue, 3 red. Basically 6 and 3. And another combination that worked was 1 red and 3 blue. So 1, 3, 6, 10. Does that sound familiar to anybody?
Pascal's triangle. We figured it out.
Triangular numbers.
Pascal's triangle.
Wow, that's kind of cool. So I want to ask the last group in the back to come up and share what they've been working on, because they kind of jumped into this, but then I forced them to step back and make sure they all could make sense of it. So can you just come up and share? I know we don't have time to get into the deep part of it, but what they did is instead of taking 6 for one of the tiles and n for another, they said, well, let's just give them both variables, b and r, and throw that into our probability calculations and see what happens. So can you just come up and share that briefly? And then I need to wrap up. They're going to bring out the hook.
You're talking. They came up with they're going to be like, what?
Oh, it'll face you. Turn it to face you.
Actually, I'm excited. I can zoom out because I'd like to know more about relations.
Yeah.
Nobody wanted
So just real quick, if you could give your attention to this group that's sharing.
So we got rid of the numbers by just using B as blue and R as red. So the probability of getting a blue, or getting 2 blues, is B over B plus R. That's picking the first one, and the second one minus 1. And we kind of grouped these together just so that later on when we multiply it's easier. We don't have to distribute everything. And then the red, similarly, just the top is red. So you either pick 2 blues or 2 reds. And we.
So just pause. Everyone okay with that first step?
Everyone okay with the first step? Well, we're saying this needs to equal to 1/2. So we did a lot of algebra. Multiply the top and the bottom. The way that we did it was just seeing this as x, and this is as x minus 1, so it's x squared minus x. That way we didn't have to do all of that. Then we regroup these two, the square terms together, and then the single terms together. So they have some sort of form equal to 1/2. Then we did the cross multiply, because we know that it can't be 0 anyway, because that way the game can't win. So we cross multiply, and we did a whole lot of other math, a lot of it. And we came up to this part right here, where the difference between b and r squared equals the sum of b and r, which tells us that the sum of the total number needs to be a perfect square, because otherwise you can't square. So we started exploring perfect squares, like 4, 9, 16, 25, and then when the table thing is, you can't see the bottom half of the table. See, there's lots of D's and S's. It's interesting if you look at, well, we thought it was interesting, if you look at this sideways, the S's all form a triangle, right? It's like the Pascal triangle. And the S's over here also form a Pascal triangle. So if you think about those numbers, those are the numbers.
When we saw the triangle, then we started going, well, if we had 10 and 6.